All right, let's continue here with hydrostatic pressure. I hope you watched the other separate video on hydrostatic pressure at depth h. Okay, so I have here a question related to that. So what is the pressure at the bottom of a 10-meter deep swimming pool? So here is a few things here. So here, very important thing. So by now you guys have probably learned the most important thing in physics is always writing down the given information. Here, identifying the unknown quantity, drawing a picture. That is, that would be helpful for us to answer our question, right? So let's see. So let us read. Okay, I'm gonna just do this here. What is the pressure at the bottom? Okay, so I'm gonna write what is the pressure as P equal to what, okay, at the bottom of a 10-meter deep. Okay, so this 10-meter deep meaning it is, we are given height equal to what, 10-meter, right, deep swimming pool. Now I'm going to make a swimming pool. If it doesn't look like a swimming pool that you have seen, please forgive me. So I'm gonna make it somewhere just here, tiny swimming pool. Alright, so this is a swimming pool. Does it look like a swimming pool to you guys? Let's say there is this, fluid, water really. I don't think you want to swim in the mercury, right? So water, let's say that has a density rho. Let's consider this, height as h. This h is same as this h, and then we want to find what's the pressure somewhere down here at this, maybe somewhere here. Let's say this point. This is what's the pressure P, this quantity, okay, pressure. That looks like a rho, so let me rewrite again. What's the pressure there, okay? So what else do we need? What do we know? How to find the pressure at this depth? Okay, so now we know, first of all, let's look at it. This liquid or this water, is it moving? No. What does that tell us? If it is not moving, then it is the case of hydrostatic condition, or this water is at equilibrium. So now we know we need to use, so let's write, we know pressure, hydrostatic pressure equation is what? P equal to P naught plus what? Rho G H, right? I'm writing this P naught. What is this P naught? Well, in swimming pool also, there is air on the top, so really this, there is a P naught is here, right? The atmosphere is pressing it. So basically we have that pressure P naught, which is about 1 atm, right? Okay, so we have this. Now let's look at what are the quantity we have at hand. P naught is something, it's constant, we can use that one. Rho is not given here, but rho is a constant, right, for water, so regular water. So what we are going to do is we are going to use this we looked at earlier, density of a fluid. I'm going to pick a water, it has a density 1000, okay? So that rho, let's write this down. Rho is here 1000 kg per meter cube. P naught is also what? Let's write down. P naught is also 1 atm. We also learned what 1 atm means earlier. We learned it should be close to 1.01 into 10 to the power 5 Pascal. Okay, it is equal to 1 atm. 1 atmospheric pressure is equal to this. You may see 1.013 times 10 to the power 5 Pascal, but let's use just three significant figures here for now. Okay, so now we know this. Do you guys know what is this Z? I hope you know by now, right? That's the acceleration due to gravity, right? So you guys know the value of that g. We are given it. Now see, it's easy. So now let's just substitute these all known quantities and find out this unknown. So this tells us P, I hope you guys can see this, P equal to what? So 1 point, in place of P naught we have 1.01 into 10 to the power 5 Pascal, right? So this is this quantity we have here plus, oh, I'm not going to write down all this unit here, okay? I'll write it at the end because all of this should give us some Pascal quantity here, okay? Plus what is this? Rho is what? 1000 times g is 9.8 meter per second squared times height is 10 meter, okay? So now if you do the calculation here, what do you get here? .99 into 10 to the power 5 Pascal, okay? So just try this out here, try this, okay, all right. So you see this is about 2 times, or really 2 kilopascal, right? No, is it? Yes, okay, or let's say 2 times 10 to the power 5 Pascal. Is this like reasonable pressure? At that depth, at 10 meter, it's pretty reasonable. It's large quantity here, 10 to the power 5, right? Okay. All right. So guys, please practice some of the questions from example problems from your textbook, okay? That will help you guys to, you know, get better at solving problem in this chapter. Do you think you have any question here? If you have any question regarding this, make a note somewhere there and then please post it into class discussion page. Now another thing that would be helpful is after we are done with this video, try just doing this question again without looking at the answer and see if you can do it yourself. And then if you try it today, if you can do it today, you will be able to do it tomorrow, okay? Okay, so all right, let's look at this. There are these vessels, 4 of these vessels, but then they have a, you know, they are all connected through this horizontal tube here, okay? So this is connected to this is connected to this, and this is connected. They are connected to each other. Let's say you decide to pour, I don't know what do you want to pour here. Let's say, assume you pour some oil. No, maybe not. Let's say some dishwashing soap that's like red in color, okay? Let's say, what do you think happens? The color is not important here, okay? So I just said that so you can visualize better. What do you think would happen if you pour you know, liquid here? Do you think that liquid you know, in this vessel would be at the same height as this one, or they will be, maybe liquid here is go up, and then because it's tiny vessel, and then it should be like probably down here, and then here they kind of have a different shape. So maybe here, I don't know, maybe it would go here, or maybe it would go here, or maybe all of them would come at the same height. What do you think would happen? Okay, so the result, are you ready to look at this result? It turns out that like this. Oh, You see the reason there is the red, because I just had this picture here and I wanted you to visualize the red color. Okay, so the color is not important. So the result is this here: a connected liquid in hydrostatic equilibrium rises to the same height in all open regions of the container. So you see all of them are at the same height, same height, same height. Please don't mind this little red here, that was not supposed to be part of this here. Okay, okay, so now we are going to learn few things, more interesting thing here. Oh, another thing is also, so if we are to pick a point, there is this horizontal line. If you want to find a pressure at this point here, at this point here, at this point here, and at this point here, which are at the same horizontal line, the pressure is going to be same. Okay, irrespective of which tube we are in, the pressure at the same height is equal. Okay. Oh, important thing, this liquid has to be a single kind. Okay, so the liquid of a single kind. If we had something else here, maybe I don't know, kerosene oil or maybe gasoline, it would not be the same case. Okay, so a few minutes ago, earlier, I said the unit of the pressure is a Pascal. Here is a Pascal. Well, not Pascal, actually, picture of Pascal. Okay, so his full name is Blaise Pascal. He was a French philosopher, mathematician, physicist, theologian. Some of the interesting saying from him are here. So, kind words do not cost much, yet they accomplish much. Small minds are concerned with the extraordinary, great minds with the ordinary. The struggle alone pleases us, not the victory. Guys, this line this is what the physicists are always doing. The struggle alone pleases us, not the victory. We are not much concerned with the results. We are more concerned with the process. Okay? The last one here, the strength of a man's virtue should not be measured by his special exertions, but by his habitual acts. So let's look at what was his contribution in the field of fluid. Okay. So that will bring us to something called Pascal's principle. So this is a principle formed by Pascal. It goes like this: if the pressure at one point in an incompressible fluid is changed, the pressure at every other point in the fluid changes by the same amount. So what does that really mean? It really means something like this. Okay, maybe I think I would show you guys. We have here some fluid here, and then let's say it has some pressure P here, but then somehow we change the pressure here. Let's say maybe somewhere here on the top. Okay, initially we had a P naught, let's say here, and then we had a P here, but then initially this was P naught, but somehow we change the pressure here. Let's say some change is like delta P. Okay, then even though we change just here, but then that means that pressure, that this change in delta P affects everywhere. So in every part of this, the change is the same value. Okay, so delta P. basically. So okay, well, you're saying something delta P and so on. I don't know how is this relevant to life, real life. Okay, all right. If you think that way, then imagine you were, you have a balloon, and then imagine you fill the water, okay, in a balloon. Probably you blow it. I guess that should also work, but I'm visualizing. Maybe visualize a polythene bag, okay, like this thin polythene bag you get from, I don't know, like Safeway or Walmart or somewhere, and you pour some water there, and then you made it tight on the top, and then let's say then you start to squeeze it. Oh, and then you made some hole in that. What do you think would happen? From each of those hole, the water is going to flow, right? And then, so because as you squeeze, what happens, that change in the pressure has to be imparted to every point in the fluid, so that you will be able to see that when you squeeze more, then all the waters are gonna come out from those different hole. Whatever pressure you applied, that change has to be there for the whole fluid. Okay, so that's the one of the example. Now let's look at application of this Pascal's principle. So application of Pascal principle. Application, pressure gauges. Pressure gauges, there is one, let's just write one called manometer, MANOMETER. You see this meter, right? Mano and meter. So this really means pressure meter, okay? Pressure meter. Manometer is an instrument you use to measure the pressure of the fluid. I have a picture here, right here. Okay, so but I'm gonna draw it here on the board so we can look at what's the pressure. So we can derive equation for pressure. Okay, so let me try to draw this manometer. Maybe I will draw it on this side. Let's start here. Okay, let's make it like okay. Alright, let's divide this into different region. Let's say this is a region 0.1, and then 0.1, let's say there is this other 0.2, let's say the other point at the same horizontal line as 3, and let's say this part is 4. Now here we just have a atmospheric pressure, okay, so this is just, let's say, P naught, basically P atmospheric pressure. This part is usually filled with either water or mercury, okay, of density rho, and then let's represent this height as h, and then this part is filled with the gas, okay. Yeah. Now here, so what are the things we have here? Let's look at this diagram. Can we find the pressure here? There is this fluid, this is at a height h, and then there is atmospheric pressure. You should be able to find this fluid, right, using the hydrostatic pressure equation, because this fluid is not moving, okay. So if you can find that pressure, then look at this. That pressure at this point 2 must be equal to the pressure at this point, because they are at the same height. If we draw imaginary horizontal line here, they should have the same pressure, right? So whatever the pressure we have here, we can equate with that pressure with the pressure here. But this pressure at this point is really, this layer is actually in touch with the gas, so that at that point the pressure should be really the pressure of the gas pressure. Okay, so that is the concept we are going to use here. So let's look at here. At point, so at point 2 P2, we can say P2 equal to what? P naught plus rho ZH, right? Hydrostatic pressure equation. Pressure equation, that's what we used here. Let's call this equation 1. P naught is really atmospheric pressure, right? This P naught is really P naught equal to what? P ATM. We are going to replace with that in another step here. Okay, so but P2 must be equal to P3, since this, you know, dot, this means since. Okay, this is this, have you guys seen? This means therefore the opposite of that is like this, means upside down, is that's called since. Since pressure said, since they are at same height, they are at same height, make this separate, that's like a scratch. Okay, same height. So now let's use this equation. So let's call this 2. So from 1 2, and then we also want to substitute what is this value of P naught. Okay, then we can write what next step is gonna be. P3 must be equal to P naught plus rho, P ATM plus rho ZH. But guys, I said P3 is also what? Pressure of the, this P3 is but again another but here, P3 is in, maybe not P3, 3, region 3 is in contact with gas, so the pressure P3 must be equal to P gas. Okay, alright guys, I have to, you know, my board is kind of tiny, so I have to go, I'm gonna erase what we have here. Okay, so if you are, you know, writing this down or copying this down, please finish copying this. Okay, I'm gonna erase this part here. So you see, in place of P3 we are going to replace with P gas, so that will give us what? P gas equal to P ATM plus rho ZH. And then we want to rearrange this. Let's write rho GH equal to P gas minus P ATM. So this here, this quantity here is usually called as a gauge pressure, G-A-U-Z-E, gauge pressure. So this is different from atmospheric pressure. Okay, gauge pressure is not same as atmospheric pressure. All right. Okay, so again, gauge pressure is what? Rho GH, and is given as the difference between the gas pressure and atmospheric pressure. Okay, so another application of Pascal's principle. So another application of a Pascal principle is this. Probably you guys are familiar with this, since you guys are, many of you are medical biomeasures. So another application is this maybe you guys know how to say this better. Let me try. Sphygmomanometer. So this is basically a pressure gauge. Okay, sphygmo means pulse, and this is a Greek word. All right, let us see how far we are in terms of time. We can do a little bit today. I had this topic here to start on Thursday, but I think we can do it today. So let me try a little further away. Never mind, please don't mind this part. Okay, so another example here we have is another instrument that is used to measure atmospheric pressure. Okay, so manometer is used to measure, like, gauge pressure. Here is really the pressure of a fluid. This barometer is basically an instrument to use atmospheric pressure. So barometer. So assume we have this imagine we have this fluid or liquid here with density rho that is filled. Okay, and then what we are going to, and then there is also this fluid here in the container. What we are going to do is we are going to seal this with the thumb and then invert it and then put it inside here. So what is going to happen next is this. Okay, this picture. So here again we inverted this tube. So what happens is some of this fluid we had all the way up here, that's going to go out here and then go outside in the container, and then the vacuum is created here. Okay, so if it's vacuum, it means pressure is 0. Okay, and then now let's assume 2 points here, 0.1 here, and then 0.2, which is inside this tube, but it is at the same horizontal distance, same horizontal line or same height. Let's call this as 0.2. This 0.2 is at 0.2, the distance between this 0.2 and this top of this fluid is h. So now because this 0.1 here, this is exposed to the atmosphere here, so let's say the P1 as a pressure at this 0.1, which is equal to what? P atmospheric pressure. Okay, and then at 0.2, let's call that pressure at 0.2 as P2, and which is given by what? Rho GH, right? Because we don't have anything. Usually we used to have a P naught here, but it's vacuum, so there is nothing, so all we have is rho GH. This is again comes from hydrostatic pressure equation, because this fluid is at rest, okay, or not moving. So now we have P1 equal to what? P ATM. I'm just gonna write P, okay, ATM always for that, and then P2 equal to rho ZH. But P1 and P2 are at the same height, right? Or they are along the same horizontal line. P1 must be equal to P2. Okay, let me move this guy a little bit that way. Okay, so this really means what then? P1 is what? PATMOS. Really, I just write PATM, guys. It's just big, as long as you're consistent, it does not matter. Okay, PATMOS or PATM. Okay, so PATM mu is equal to what? P2, right? So that must be equal to rho gh. So this is how we can use barometer. So this equation gives us atmospheric pressure, equation for it, atmospheric pressure. Okay, so this is the equation for atmospheric pressure, and then we can use the barometer to measure atmospheric pressure by measuring the height of the liquid in a column, okay, or in that tube basically. Atmospheric pressure, useful again useful unit is, we said it's atm, right? 1 atm equal to 760 mm of Hg. Again, this mm of Hg means millimeter of mercury rising in a tube basically, okay? And then this value is also equal to 760 torr, so you could really see that, right? 1 atm is same as 760 mm of Hg, or 1 atm is also same as 760 torr. Okay, basically this was invented by Evangelista Torricelli in 1644. He was the inventor of barometer. Okay. Alright, I think we'll stop here for today, and we'll start the topic buoyancy on Thursday. Alright.